Team, this is a review on DC circuits and Kirchhoff's rules. So first off, let's start off by reviewing the problem. It says calculate the rate at which R3 dissipates energy. I am already identifying that since it is R3, I am going to use loop 1 around because it covers R3. Also notice that I am given R2. I am given R4. I am given V3. And I am also given current 3 and current 1. Because I am given this, all I need to do, once I do Kirchhoff, is solve for R3. I am not given I2, but this is where our PRC equations come in. So remember, we have our PRC equations where this is the voltage across the resistor equals the current going through the resistor times the resistance of the resistor. Since it is a rate which dissipates energy that we need to calculate, it is an equation of power. And if we substitute V with IR, we get our famous equation, which is P equals I squared times R. Now, this one is part of Kirchhoff, where it says that if we have a junction, like this one right here, where we have I, and let me point it out right here, I1 and I2 and I3. So in this situation, it seems like I1 and I3 are going into the junction and only I2 is coming out. So we would write this, and this is for step one, where step one begins. Step one, solve for current 2, because we need current 2 for solving for the current across the resistor in 3. Solve for current 2, and we write down everything going into the junction, which is I1 plus I3 equals I2. In, out. Because of that, because we have I1 and I3 already, boom, you're done with solving for I2. You got I2. I am not going to just solve the number. I'm just going to give you the answer algebraically. Okay, so now that you have that, let us go for step 2. Step 2 is solve for R3. And we use Kirchhoff's rules. So I already told you about loop 1. But just remember, getting closer to here, and I am going to write down that high equals, or H equals high, and L equals low. And I am just going to do this for the sake of, so you can see how my way of thinking is. So whenever we're passing through Kirchhoff, when it comes to a battery always starts low and then goes to high. Okay? And because of that, since I'm doing Kirchhoff, and this is Kirchhoff right here, this is my loop. Because of that, I subtract, I do a change, which is the electric potential, the high electric potential, minus the low electric potential equals a positive I V3. I'm going to write it right here, my positive V3. Now, the direction of current, which is denoted right here for I3, is telling me that it's going upwards. So this is I3. The direction of current in a resistor tells me that because it's going in this direction, it means that my resistor starts high and then after it passes the resistor goes low. But we're passing through a battery now, and that battery, it is telling me with the plus signs, it is telling me that this has a high electric potential here and a low electric potential here. Passing again, current in I2 is telling me that current is going this way because current is going in this direction, and current always goes, for a resistor, current always goes from high to low. We have high here, low here. Then the resistor 4 starts from high and ends up in low. So reviewing after V3, reviewing R2, since we end up with low, but we start with high, low minus high electric potential gives me a negative voltage across resistor 2. Now, passing the battery V2, I end up with a low electric potential right here. So low electric potential minus high electric potential gives me a negative V2. Going now for resistor 2, I have a low electric potential here minus a high electric potential gives me a negative voltage across resistor 3. And finally, the same goes for voltage across resistor 4. And that all equals to 0 according to Kirchhoff, that said that if you do a loop around a closed circuit, the summation of the change of electric potential would equal to 0. So now what we have to do is make sure that we have our substitutions. So the voltage across resistor 2, it is I3, because the current, right, the current here passing through that section is I3 times R2 minus V2 minus voltage across resistor 3, so that is I2 times R3. Sorry, let me erase this. There you go, R3. And then again, minus I2 times R4. And the reason again is because the current here, current 2, is taking over this section right here. All right, erasing this, and that all equals to 0. Okay, so now all we have to do is solve for R3, which equals V3 minus I3 R2 minus V2 minus I2 R3 over I2. And that is your algebraic answer for resistor 2. Now it's also asking us, well, it's actually asking us to solve for the dissipation of energy, meaning that we have to use the power. It is the power is energy dissipated. So step 3, solve for power. And that is only because it is energy dissipated at 3. We are caring for the current I2 squared times R3. And this equation, just like we spoke of right here, that's where it comes from. All right, this concludes our our topic on DC circuits and Kirchhoff's rules.